Yeah, sir.
Good morning to everyone. Welcome to webinar class, chapter number 7, chemical equilibrium, acids and bases. Previous class completed law of mass action, Kc and Kp relationship between reaction constant K, quotient Q, free energy G. Today class, chemical equilibrium, acid bases, types of equilibrium. Types of equilibria. Types of equilibria based on physical states of reactant and product. There are two types of equilibrium. Number one, homogeneous equilibrium, and second one is heterogeneous equilibrium. Equilibrium based on physical states of reactant and product. Okay. Number one, homogeneous equilibrium. What is homogeneous equilibrium? The chemical equilibrium in which both reactants and products are in the same physical state. The chemical equilibrium in which both reactants and product are in the same physical state, liquids or gases or aqueous solution, is called homogeneous equilibrium. Same phases, a product and reactant and product. Example, homogeneous equilibrium example number 1, H2 plus I2 gives rise to 2HI. Here reactant H2 and I2, product 2HI, same physical state, gases phase. So this equilibrium is called as homogeneous equilibrium. Second example, 2HI gives rise to I2 plus H2. So same phases, physical state, reactant and product. And two, next example, 2NO2 gives rise to N2O4, reactant NO2 and product N2O4, same physical state. So this equilibrium is called as homogeneous equilibrium. Okay. Next example, PCl5 gives rise to PCl3 plus Cl2. Here, reactant and product same physical state. Ethyl acetate CH3COO C2H5 plus H2O gives rise to CH3COOH acetic acid plus ethyl alcohol C2H5OH. Here reactant and product are same physical state. These equilibrium above examples are homogeneous equilibrium. Okay, next one, homogeneous equilibrium example, another one, Fe plus 3 plus SCN minus gives rise to Fe SCN taken 3, ferrous thiocyanate. Ferrithiocyanate, they are reactant and product same physical state. What is heterogeneous equilibrium? Heterogeneous equilibrium means the chemical equilibrium in which both reactants and products are in different physical states is called heterogeneous equilibrium. The chemical equilibrium in which both reactant and product are different physical states. Same physical state is called as homogeneous equilibrium. Different physical states is called as heterogeneous equilibrium. Examples here, heterogeneous equilibrium number 1, calcium carbonate CaCO3, solid physical state, gives rise to CaO plus CO2. Here CaCO3 solid physical state, CaO physical state solid, CO2 is gases physical state. So they are different physical state, reactant and product. These equilibrium is called as heterogeneous equilibrium. Another one example, 4H2O plus 3Fe gives rise to Fe3O4 plus 4H2. Here, reactant and product both are different physical state. It is also heterogeneous equilibrium. Zn plus CuSO4 gives rise to ZnSO4 plus Cu. Here, reactant and product different physical state. Next one example, NH4HS gives rise to NH3 plus H2S. NH4HS solid state, NH3 gaseous state, and H2S also gaseous state. Here, reactant and here product to different physical state. This equilibrium is called as heterogeneous equilibrium. Mathematical approach to find Kc. Here, mathematical approach to find Kc If initial moles are given and equilibrium constant for gases equilibria, let us consider the following equilibrium. If the initial moles are 1.01, each let x moles of each be converted into product. Here example, H2 plus I2 gives rise to 2HI. Initial concentration 1 reactant and product concentration is 0. At equilibrium, reactant 1 minus x, H2 concentration 1 minus x, product concentration 2x at equilibrium. Okay, concentration is equal to N by V. So here 1 minus x by V, reactant concentration at equilibrium, 1 minus x by V, product concentration 2x by V. Apply these terms into Kc, expression of equilibrium. Kc is equal to molar concentration by reactant concentration, product molar concentration by reactant molar concentration. The product molar concentration Kc, here HA molar concentration is equal to 2x by 2x whole square by 1 minus x into 1 minus x. Therefore, Kc is equal to 4x square by 1 minus x whole square. This is Kc. Kp, apply this term into Kp expression of equilibrium. The total number of moles 1 minus x plus 1 minus x plus 2x. Here 1 minus 2 minus 2x. 2x cancel. That equal to total number of moles is equal to 2. Let the total partial pressure be P. Here mole fraction is equal to number of moles by total number of moles. Let the partial pressure H2 reactant partial pressure is equal to H2 number of moles to 1 minus x by total number of moles to 2. The next, let the partial pressure pH2, partial pressure of H2 P into 1 minus x by 2. Partial pressure of I2 is equal to number of moles of I2 1 minus x by total number of moles 2. Therefore, P into 1 minus x by 2. PHI, partial pressure of HI is equal to partial pressure of number of moles of HI 2x by total number of moles 2. 2 to cancel. Therefore, Px, number of moles of P square HI is equal to P square into x square. Therefore, apply these terms in the Kp expression given below. Kp is equal to partial pressure of product by partial pressure of reactant, partial pressure of product to HI by partial pressure of reactant, partial pressure of H2 into partial pressure of I2. Therefore, apply the Kp is equal to partial pressure of HI is equal to x square P square x square by 1 minus x by 2 into partial pressure P, 1 minus x by 2 into partial pressure P. Therefore, 4x square by 1 minus x whole square. Therefore, in this case, Kp is equal to Kc. Now, prove the Kp is equal to Kc. The mathematical approach to find Kc, if initial moles are given, let us consider dissociation of PCl5. Let us consider the following equilibrium. Okay, student, listen here carefully. If the initial moles are 1, each let x moles of each be converted into product. So, for example, PCl5 gives rise to PCl3 plus Cl2. Initial concentration 1, product concentration 0. At equilibrium, initial concentration of PCl5 1 minus x, product concentration x and x. Here x by V, N by V means number of moles by V value. So 1 minus x by V, here x by V, x by V at concentration at equilibrium. Apply these term Kc expression of equilibrium. Kc is equal to the molar concentration of product by the molar concentration of reactant, product PCl3 into Cl2 by reactant molar concentration PCl5. That equal to the molar concentration of PCl3 is equal to x by V. Cl2 concentration x by v by 1 minus x by v, that equal to x square by 1 minus x into 1 by v. Therefore, x square is equal to kc into 1 minus x into v. Therefore, x is equal to square root of kc into 1 minus x into v. Apply these terms into Kp expression of equilibrium. Total number of moles is equal to 1 minus x minus x, that equal to 1 plus x. Let the total partial pressure P, the mole fraction is equal to number of moles by total number of moles. The partial pressure of PCl3 is equal to partial pressure of P into x by 1 plus x. Partial pressure of Cl2 is equal to partial pressure of P into x by 1 plus x. Partial pressure of PCl5 is equal to number of moles of PCl5, total number of moles, partial pressure into 1 minus x by 1 plus x. Kp is equal to partial pressure of product by partial pressure of reactant. Apply the partial pressure. Kp is equal to P into x by 1 plus x into P into x by 1 plus x by P into 1 minus x by 1 plus x. Kp is equal to P x square by 1 minus x square. Therefore, Kp into 1 minus x whole square is that equal to Px square. Kp minus Kp x square, that equal to Px square. Kp is equal to, okay student, Px square plus Kp x square. Common factor x square Kp plus P into x square. X square is equal to Kp by Kp plus P. X equal to K square root of Kp by Kp plus P. That is the next topic goes to equilibrium constant for general reaction and it multiplies. Equilibrium constant chemical equation A plus B gives rise to C into C plus D into D, Kc. Then next backward reaction C plus D, that gives rise to A plus B, Kc1 equal to 1 by Kc. Number of moles, so Na plus Nb gives rise to number of moles C plus Nd, Kc2 equal to Kc number of moles N. Here, equilibrium constant Kp for few selected reaction N2 plus 3H2 gives rise to 2NH3 at temperature 298 Kelvin, Kp value 6.8 into 10 to the power of 5, temperature 400 Kelvin, Kp value 41, 500 Kelvin 3.6 into 10 to the power of 2, N2O4 gives rise to 2NO2 at temperature 298 Kelvin, Kp value 0.98, 400 Kelvin, Kp value 47.9, at temperature 500 Kelvin, 1700 Kp value. Units of equilibrium constant. Kc units mole per liter power delta N. Kp units atmosphere per delta N. Delta N equal to number of moles of product minus number of moles of reactant. Once again, Kp delta N is equal to number of moles of product minus number of moles of reactant. For gases equilibrium, delta N is equal to number of moles of gases product minus number of moles of gases reactant. Okay, units for the following equilibrium. Example, CaCO3 gives rise to CaO plus CO2. Delta N is equal to the number of moles of product minus number of moles of reactant in gaseous state only. Therefore, product number of moles only 1. CO2 is gaseous physical state. 1 minus 0, that equal to 1. Kc is equal to molar concentration of CO2 power 1. Units mole per liter. Next example, PCl5 gives rise to PCl3 plus Cl2. Kc is equal to molar concentration of product by molar concentration of reactant. Kc equal to PCl3 units mole per liter. Cl2 molar concentration mole per liter. PCl5 molar concentration units mole per liter. Mole per liter get cancelled. the Kc units mole per liter. Delta N is equal to here number of moles of product PCl3 and Cl2 1 ante 2 minus PCl5 number of moles 1 2 minus 1 that equal to 1. Kc is equal to units mole per liter, therefore units mole per liter. Next example, H2 plus I2 gives rise to HI. Delta N is equal to the number of moles of product minus number of moles of reactant. Number of moles of product is equal to 2 minus number of moles of reactant 1 plus 1 2. 2 minus 2 that equal to 0. Kc is equal to no units because of delta N is equal to 0. Kc is equal to number of moles of product by number of moles of reactant, N square by V square by N square by V square. Get cancel, Kc is equal to 0. Kc is no units. Kp atmosphere per delta N. Atmosphere delta N is equal to 0. Substitute the 0. A power 0 is equal to 1. No units in this equation. In the next example, 3H2 plus N2 gives rise to 2NH3. Delta N is equal to number of moles of product minus number of moles of reactant. Here number of moles of product 2 minus number of moles of reactant 3 plus 1. So 4. 2 minus 4 is equal to minus 2. Kc is equal to mole per liter whole power delta N. Delta N value minus 2. The units is liter square per mole square. Kp units also atmosphere per whole power delta N. Delta N is equal to minus 2. Atmosphere per minus 2. 1 by atmosphere whole square. So, this is the Kp and Kp units. Write the units of the following equilibrium. Fifth one example, nickel Ni solid substances plus C4CO gaseous state gives rise to nickel tetracarbonyl NiCO taken for gaseous state. Here solid substances is equal to 1. Therefore, Kc is equal to product molar concentration by reactant molar concentration. Here reactant only carbon monoxide. Nickel is a solid substance that is equal to 1. Therefore, Kc is equal to mole per liter by mole per liter power 4. So 1 by mole per liter power 3. The units is liters cube by cubic per mole. So units Kc is equal to cubic liter per mole cube. Delta N is equal to product molar concentration 1 minus reactant molar concentration 1. Here 4. 1 minus 4 is equal to minus 3. The units also mole per liter power minus cube. Kp is equal to atmosphere whole power delta N. So that equal to atmosphere whole power minus 3. Atmosphere minus cube units. Important features of equilibrium constant. It is applicable only when concentration of reactant and products have a constant value at equilibrium. It is independent of initial concentration. It is independent of initial concentration. It is temperature dependent. It has particular value at particular temperature. It is inverse of reverse process when compared to forward processes. This is the important features of equilibrium constant. For next point, the equilibrium constant K for a reaction whose equation is obtained by multiplying or dividing the equation for the original reaction by a small integer n is related to the equilibrium constant K of the original reaction K1 that equal to K power n. Application of equilibrium constant, predicting the extent of reaction on the basis of its magnitude, predicting the direction of reaction, calculation of equilibrium constant, predicting the extent of reaction. Most must to remember this point to predict the extent of reaction. The magnitude of Kc or Kp is directly proportional to the concentration of products and inversely proportional to the concentration of reactant. Here once again repeat, the magnitude of Kc or Kp is directly proportional to the concentration of products and inversely proportional to the concentration of reactant. Here number one, if Kc is very large, Kc is greater than equal to 1, the reaction nearly proceeds to completion. If Kc is greater than 10 to the power of 3, product concentration is more than reactant concentration. Suppose if Kc is very small, Kc is less than 1, the reaction rarely proceeds. If Kc is less than 10 to the power of minus 3, reactant concentration is more than product concentration. Suppose if Kc is in the large of 10 to the power of minus 3 to 10 to the power of 3, appreciable concentration of both products and reactant are present. One question is, the reaction between hydrogen and oxygen at 500 Kelvin has Kc is equal to 2.4 into 10 to the power of 47. Comment on this. The reaction nearly goes to completion as the Kc value is very large. Kc value is very large. Okay. Here summary. The picture depends of extent of reaction Kc. Kc, see the diagram, negligible 10 to the power of minus 3, Kc is equal to 1, 10 to the power of 3, extremely large, both reactant and product are present at equilibrium. Here predict the direction of reaction. To decide the direction of reaction apart from Kc, we need Qc, reaction quotient. Here, what is reaction quotient QC? QC expression is similar to Kc expression, excepting that for Kc, Rf is equal to Rb. Forward reaction rate is equal to backward reaction rate, whereas QC, Rf is not equal to Rb. Here, Rf is the rate of forward reaction, Rb is the rate of reverse reaction. Once again, QC expression is similar to Kc expression, excepting that for Kc, Rf equal to Rb, whereas QC, Rf is not equal to Rb. Here, general reversible reaction A plus B gives rise to C plus D. QC is equal to molar concentration of product by molar concentration of reactant. Here predicting the direction of reaction. If QC is greater than Kc, Rf, forward reaction rate, is not equal to backward reaction rate, and product concentration is more than reactant concentration. Once again, if QC is greater than Kc, Rf is not equal to Rb. It means forward reaction rate is not equal to backward reaction rate, and product concentration is more than reactant concentration. To attain equilibrium reaction, it takes place in the forward direction. Reactant formation is favored. Reaction moves from right to left. If QC is less than Kc, Rf is not equal to Rb, and reactant concentration is more than product concentration. QC is less than Kc, Rf is not equal to Rb. It means forward reaction rate is not equal to backward reaction rate, and reactant concentration is more than product concentration. To attain equilibrium reaction, it takes place in the forward direction. Product formation is favored. Reaction moves from left to right. Suppose predicting the direction of reaction. If QC is equal to Kc, Rf is equal to Rb, and reactant concentration is constant, and product concentration is also constant. Thus, reaction system is an equilibrium. No net reaction occurs. Suppose example H2 plus I2 gives rise to 2Hi. Equilibrium concentration 0.1 m, 0.2 m gives product 0.4 m. Concentration Kc is equal to 47. Qc is equal to the molar concentration of product by molar concentration of reactant. 0.4 into 0.4 by 0.1 into 0.2. That equal to 16 by 2. Qc is equal to 8. Kc is equal to 47. Here, since QC is less than Kc, The reaction proceeds in the forward direction until equilibrium is attained. Qc become equal to Kc numerically. Therefore, is favored forward reaction. Here, see the diagram QC and KC relationship representation diagram. Here, QC is less than KC. Reactant gives rise to product. QC is equal to KC. Reactant and product at equilibrium. QC is greater than KC. Reactant gives rise to no, product gives rise to reactant. Once again, repeat. QC less than KC. See the diagram. Reactant gives rise to product. Here QC is equal to Kc. Reactant and product are equal at equilibrium. QC is greater than Kc. Product gives rise to reactant. Okay. And the next topic is Le-Chatelier principle. What is Le-Chatelier principle? If a chemical reaction at equilibrium is subjected to change in temperature, pressure, or concentration, that the chemical equilibrium. The equilibrium position shifts in the direction in which the change is nullified or reduced. Once again, it states that a change in any of the factors that govern the equilibrium condition of system will cause the system to change in such manner so as to reduce or to contract of effect of change. It means change in temperature, pressure, or concentration, that the chemical equilibrium, the equilibrium position shifts in the direction in which the change is nullified or reduced. Here, effect of concentration change. Effect of concentration change. Here, when concentration of reactant increases, when concentration of important topic, Le-Chatelier principle, listen carefully, student. When concentration of reactant increased, the equilibrium shifts toward right, favor the forward reaction. And it means increasing concentration of reactant in the reaction mixture at equilibrium favors the forward reaction to form product. To remove the effect of increase to keep Kc value constant. The next effect concentration change, decrease in concentration. Suppose when concentration decreased, concentration of product is decreased, the equilibrium shifts toward right side, favor the forward reaction. It means decreasing concentration of reactants in the reaction mixture at equilibrium favored backward reaction. Reactant concentration decreases. Here, when concentration of product decreased, the equilibrium shifts toward right side, favor forward reaction. Here, concentration of reactant increased, favor forward reaction. Concentration of product decreased, forward reaction. Effect concentration change. When concentration of reactant decreased, the equilibrium shifts toward left side. It means favor the backward reaction to form reactant to remove the effect of decrease to keep Kc value constant. It means decrease in the concentration of reactant in the reaction mixture at equilibrium. Reaction mixture at equilibrium favored backward reaction. Increasing the concentration of reactant favor forward reaction. Decrease the concentration of reactant favored backward reaction. Okay, listen carefully. Concentration. When concentration of product increased, the equilibrium shifts toward left side, favor the backward reaction. In, when concentration of product decreased, favored forward reaction. When concentration of product is increased, the equilibrium shifts towards left side, favors the backward reaction to form reactants to remove the effect of increase to keep Kc value constant. This is concentration, effect of concentration. Effect of concentration change. Let us look at this effect mathematically for the equilibrium equation. H2 plus I2 gives rise to 2HI. Kc is equal to molar concentration of product by molar concentration of reactant. HI for concentration power 2 by reactant concentration H2 concentration into I2 concentration. Effect factors affecting or influencing the equilibria. If we increase H2 molar concentration or I2 molar concentration or both Kc value decreases as they are inversely proportional to Kc. However, Kc value is constant at particular temperature. To keep Kc value constant, equilibrium shifts to right by converting reactant into product. Thus, a new equilibrium is established. This effect of concentration. See the graph effect of concentration equilibrium re-established. H2, I2, HI. H2 is added, not equilibrium. See the diagram. Effect concentration and experiment. Let us consider a reaction whose equilibrium can be observed by a color change. Color change. The reaction between ferric ion and thiocyanate ion gives deep red colorization, which can be equilibrium state. Ferric yellow color, thiocyanate colorless, gives rise to ferric thiocyanate deep red color. Kc is equal to ferric thiocyanate product molar concentration by reactant molar concentration. A reddish color appear on adding 2 drops of 0.002 moles iron nitrate solution to 1 mole of 0.2 potassium thiocyanate solution due to the formation of ferrous thiocyanate. Here, experiment observation. The inversely intensity of red color become constant on attaining equilibrium. This equilibrium can be shifted to right by adding reactant. As a result, color intensity is increases. When oxalic acid is added, the color intensity decreases as oxalate ion react with ferric ion to form ferric oxalate. As a result, Fe plus 3 ion concentration is decreases. Effect concentration and experiment. When Fe plus 3 ion decreases, the ferrous thiocyanate complex dissociate to give Fe plus 3 and thiocyanate. Thus shifts the equilibrium left to maintain Kc value constant. Thus red color intensity decreases, indicating the shifts of equilibrium to the left side. Here effect of pressure and on gases equilibrium. Effect of pressure. Le Chatelier principle. What is Le Chatelier principle? If a chemical reaction at equilibrium is subjected to change in temperature, pressure or concentration, then the chemical equilibrium, the equilibrium position shifts in the direction in which this change is nullified or reduced. Second one effect is effect of pressure. Here effect of pressure can be observed in the case of gases equilibrium. Pressure influence can be observed reactant or products by decreasing the volume. In applying Le Chatelier principle to heterogeneous equilibrium, the effect of pressure changes on solid and liquid be ignored because the volume and concentration of solution or liquid is nearly independent of pressure. Here, effect of pressure. What is the effect of pressure on solid and liquid in equilibrium? In applying Le Chatelier principle to heterogeneous equilibrium, the effect of pressure change on solids and liquids can be ignored because the volume of solid or liquid is nearly independent of pressure. Here, effect of pressure. Suppose consider the reaction CO plus 3H2 gives rise to CH4 plus H2O and absorb the effect of pressure. Here, reactant carbon monoxide and hydrogen H2. Product is CH4 and H2O. The total number of moles of reactant is 4. 1 plus 3, 4. While that of product is 2 moles. 1 plus 1, 2 moles. Since there is decrease in number of moles of product, and it means 4 gives rise to 2. Product number of moles is decreases. Effect of pressure can be absorbed. Okay, student, listen carefully. Reach at the principle. Important. Delta N is equal to number of moles of product minus number of moles of reactant. Here, number of moles of product 2 minus number of moles of reactant 4. 2 minus 4, that equal to minus 2. Increase of pressure favors forward reaction. Pressure increases favor forward reaction. It means increase in the pressure of the system at equilibrium shifts the equilibrium position in that the direction in which the volume or number of moles get decreased or decrease in the volume, decrease side. So pressure is increases. Decrease pressure favor backward reaction. When delta N is equal to number of moles of product minus number of moles of reactant is equal to 0. The effect pressure is not absorbed on the equilibrium reaction as it influences both forward reaction and backward reaction equally. Effect pressure. Suppose equilibrium mixture kept in a cylinder fitted with piston at constant temperature is compressed to one half its original value, the total pressure doubled. PV is equal to constant according to Boyle's law. As the condition have changed, the system is not equilibrium anymore. To get back to equilibrium, the system has readjust itself to do so. The reaction moves in the forward direction to increase the product formation according to Leach-Attier principle. The system regain its equilibrium states by shifting it to the right. Here this can also understood by using reaction quotient QC, letter CO molar concentration, carbon monoxide, hydrogen concentration, CH4 concentration, and H2O concentration, molar concentration at equilibrium for methanation reaction. When the volume of reaction mixture is halved, the partial pressure and concentration are doubled. QC is equal to molar concentration of product by molar concentration of reactant. As QC less than KC, the reaction proceeds in the forward direction. In the reaction, C plus CO2 gives rise to 2CO. Delta N is equal to number of moles of product minus number of moles of reactant. Here 2 minus 1 is equal to 1. The reaction takes place in the backward direction with increase in number of moles gases product have taken place. Thus equilibrium shifts to the left side. It means decrease in number of moles of decrease in the pressure of the system at equilibrium shifts the equilibrium position in that the direction in which the value or the number of moles get increase in the volume. Thus equilibrium shifts to the left side. In the reaction, H2 plus I2 gives rise to HI. Delta N is equal to number of moles of product minus number of moles of reactant. 2 minus 2, that equal to 0. The equilibrium shifts undistributed as there is equal influence in the forward reaction and backward reaction direction. Kc and Kp expression are same. Effect of inert gas addition. Addition of inert gas at constant volume. If an inert gas such as argon is added to the system in equilibrium as it does not take part in the reaction, as well as pressure and concentration of reactant do not change, equilibrium remain unaffected. Effect inert gas addition at constant pressure. Suppose when an inert gas is added, the partial pressure of reactant and product is affected. So effect of inert gas depend on delta N value. If delta N is equal to 0, no effect of inert gas. If delta N is greater than 1, positive value, equilibrium moves in the forward direction. If delta N is less than 1, negative value, equilibrium moves in the backward direction. Effect of temperature change. When temperature changes, the equilibrium constant values changes while in the previous condition there is no effect on equilibrium constant value excepting the shifts of equilibrium either to the right or left. In general, the temperature depends on equilibrium constant, depends on the sign of the delta H of the reaction. Effect temperature change. For a reaction with delta H value negative, exothermic reaction of Kc equilibrium constant value decreases. Kb is greater than Kf since Kc is equal to forward reaction rate by backward reaction rate. Example, manufacture of ammonia by Haber's process. N2 plus H2 3H2 gives rise to 2NH3. Delta H is equal to minus 92 kilojoules. Effect of temperature for a reaction delta H value positive endothermic reaction value increases Kb is less than Kf. Therefore, Kc is equal to Kf by Kb. For example, manufacture of nitric acid by Berkeland-Ide process. N2 plus O2 gives rise to 2NO. Delta H value positive plus 180 kilojoule per mole. The effect temperature change when delta H is equal to 0, the equilibrium constant value remain unaffected. Change in temperature will affect the equilibrium constant. Dimerization of NO2 gas. Effect of temperature and experiment 2NO2 gives rise to N2O4. Delta H value minus 52.7 kilojoule per mole. NO2 is prepared by adding copper tunneling to concentrated nitric acid. The gas is collected into 2 5 ml test tube and escape of gas is prevented with stopper and sealing with araldite. Here, three experiment: test tube 1, test tube 2, test tube 3. Here, beaker 1, beaker 2, beaker 3. At 3 degrees Celsius, at 25 degrees Celsius, at 90 degrees Celsius. Less NO2 and more N2O4 at lower temperature, low color intensity at concentration 3 degrees Celsius, beaker number 1. Test tube 2 at beaker number 2 at 25 degrees Celsius, NO2 and N2O4 at medium temperature, same color intensity. Here beaker number 3 at 90 degrees Celsius, more NO2 and less N2O4 at high temperature, high color intensity. Here the difference between temperature. To affect temperature can also be seen in endothermic reaction. CO H2O taken 6 plus 6 Cl minus COCl6 Cl6 plus 6 H2O. At room temperature, the equilibrium mixture is blue due to hexachlorocobalt COCl6 power minus 3. At lower temperature in freezing mixture, the equilibrium mixture is pink color due to COH2O taken 6. Effect catalyst. A catalyst increase the rate of chemical reaction by making available a new low energy pathway for the conversion of reactant to product. Catalyst increase the rate of forward reaction and reverse reaction that pass through the transition state and does not affect the equilibrium. Effect catalyst lowers the activation energy for the forward and backward reaction to the same extent. Catalyst does not affect the composition of equilibrium mixture. Catalyst does appear in the balanced chemical equation or in the equilibrium constant expression. Equilibrium constant value decreases with rise in temperature. At low temperature, rate is low and takes long time to reach equilibrium. At high temperature, rate is high but yield is poor. Effect catalyst to overcome this problem, German chemistry Heber discovered that a catalyst consisting of iron catalyzes the reaction to occur at a satisfactory rate of temperature where the equilibrium concentration of NH3 is reasonably high. Here, effect catalyst optimum condition, factor favorable condition manufacture of ammonia, Haber's process, iron catalyst, temperature 450 to 500 degrees Celsius, high pressure 200 atmosphere. Okay, sir. Purity of reactant. Okay, student. Today assignment discuss the application of Le Chatelier principle for the industrial synthesis of ammonia
and sulfur trioxide. N2 plus 3H2 gives rise to 2NH3. Here, what is homogeneous and heterogeneous equilibrium? Write two example for each. Next question, why it useful to compare Q and K? What is the situation when number one Q is equal to K, number two Q is less than K, number three Q is greater than K. This is the today assignment. Okay. Thank you, student. Thank you, sir.
Okay, sir. Thanks. Complete, sir.